Good evening, everybody. Welcome to BrisScience for November 2022. My name is Joel Gilmore and I'm your MC for this evening. If this is your first time here, welcome. BrisScience is the University of Queensland's series of free public lectures on science held once a month at the fantastic State Library of Queensland. The aim of BrisScience is to bring not just the best scientists, but also the best communicators to share their research with Brisbane and, through the wonders of YouTube, the rest of the world. I would, of course, like to start by acknowledging the traditional owners of the land on which we're meeting tonight and pay my respects to Indigenous elders past, present and emerging, and acknowledge the deep connection to country and community those people have held and continue to hold to this day. Now, before we get started, a couple of bits of housekeeping. First of all, we're going to have our speaker in a moment, after which we will have some food and drink. So an opportunity for you to hang around, ask some questions, have a chat, because this should be as much a social event as going to the footy or the theatre. We also have the opportunity at the end of the talk to ask questions. So if you have your phone in now, I was really hoping that the time would work out. There is, so wrong again. So there is a QR code that you can scan. It would have been amazing if it worked though, right? There is a QR code that you can scan that will take you, hey, there it is. See, now, you can just keep that in edit, that'd be perfect. So you can scan that code, that'll take you to our Q&A page, and feel free to add the questions during the talk, or there'll be some time afterwards. We'll go through as many of those as we can. But of course, as I said, there will be a chance to chat to Ben after the talk. But if you do have your phone, if you could please pop it on silent now, that would be amazing. All right, so tonight, what are we doing? Well, just like Ant-Man, we are going to be taking a dive into the quantum realm. However, unlike Ant-Man, tonight's talk is going to be based in reality. So tonight, we are going to be exploring the concept of emergence. Now, what is emergence, I hear you ask? Sorry, we'll try that again. What is emergence, I hear you ask? Great question, and the perfect segue to introduce our speaker tonight, Professor Ben Powell. Ben has been at the University of Queensland for over 20 years. He is a theoretical physicist exploring the mysteries, perhaps of quantum mechanics. So please put your hands together for our speaker tonight, Professor Ben Powell.
Thank you all very much. So tonight I want to talk with you about the fundamentals of physics. And if I say to you the fundamentals of physics, some of the ideas that you might first think of are the large-scale structure of the universe. How did the universe begin? Why are we here? What's going on with galaxies, stars, and planets? Or you might think about the very smallest scales, where quantum mechanics dominates. You might think about atoms or subatomic particles, the Higgs boson, quarks, and leptons. You might have been told that quantum mechanics only works on the smallest scales. Well, I'm going to show you that's wrong tonight. I'm going to show you an experiment that we can only explain with quantum mechanics, and you'll be able to see it with your naked eyes. Okay. And I'm not going to talk about these frontiers of physics. I'm going to talk about, as Joel mentioned, emergence, which is a different frontier of physics. The idea that if we put unimaginably large numbers of particles together, then they can have properties that don't occur in any single particle, that are brand new properties. And two very beautiful examples of this are life and consciousness. If I take a single DNA molecule, that is not alive. If I take a single neuron, that is not conscious. It's the interactions between DNA molecules and other biomolecules. It's the interactions between neurons that give us life and give us consciousness. The field of science I work in is condensed matter physics, and we're looking at the simplest examples of collective behavior, the simplest examples of emergence. And in these very simple examples, they often occur most readily at very cold temperatures, and there we can see quantum mechanics as well. So not only are we dealing with unimaginably large numbers of particles, but they're all interacting quantum mechanically. And what I want to share with you tonight is some of the really remarkable things that happen when we have these huge numbers of particles and their interactions are dominating their behaviors of the systems. Okay, so if we think about gravity, which controls the large-scale structure of the universe, and we think about quantum mechanics, one of the very well-known problems in theoretical physics is to write down a theory that describes both gravity and quantum mechanics at the same time, the so-called theory of everything. So I thought a good place to start would be to write down, if we want to think about emergence, we can write down our theory of everything that describes gravity and quantum mechanics, and we can start from there and we can try and derive the properties. So what I did is I went ahead and I prepared a slide that says everything we know about the theory of everything, and here it is. Okay. So we don't have any theory in physics that describes both gravity and quantum mechanics. But actually, for everything I'm going to tell you, everything up to consciousness and life, that's really not very important, because gravity really isn't very important itself. So gravity is pathetically weak, and I'm going to do a nice demonstration to show you this. This is a 5-kilogram weight. It's quite heavy to pick up. The reason it's quite heavy is the entire gravitational force of the planet is pulling it down as hard as it can. Okay? These 6 things that you can maybe just about see at the back are 6 little magnets. Okay? So this magnet has a magnetic force. I can take it on the side of the thing, and I can pick up this 5-kilogram weight using a magnetic force from this tiny little magnet. And that magnet is overcoming the gravitational force of the entire planet. What's more, my muscles, which are also involved in picking that up, my tiny little pathetic muscles, again, there's electromagnetic forces that are happening in there, and I'm able to overcome the strength of the entire planet's gravitational pull. And so are you every time you walk, right? Just a simple act of walking, we're overcoming gravity. Gravity is incredibly weak compared to all the other forces. So basically, most of the time we can forget about gravity. And if we do that, then we do have a pretty good theory of everything. And that's known as the standard model of particle physics. And this is a simple summary of the standard model of particle physics. And basically, we have 4 types of particle in the standard model. We have these particles over here make up all of matter. There are quarks, which make up nuclear matter. Leptons, the most important one of those, is the electron, which is responsible for all electrical and electronic devices, for example. Then we have the force particles over here. We have the photon, which is responsible for light, also responsible for magnetism and electricity. For those electromagnetic interactions, photons are involved in picking up that weight earlier. We have things called gluons, which hold the nuclei together. And we have things called weak bosons, which are responsible basically for radioactivity and a few other more esoteric effects. And over here we have the Higgs boson, which, to be honest, actually doesn't do very much. And we'll talk a little bit about that later. But actually, in terms of the things we want to think about today, in terms of everything you can see around you, there's too much in this model. We don't need most of this. In terms of everything in this room, essentially the only particles that are doing anything are 2 of the quarks, the electron and the photon. All of chemistry, all of biology is explained by these particles. And actually, there's a very strange phenomenon called confinement. So the quarks inside of atomic nuclei are bound together very tightly, and that interaction gets stronger as you pull them apart. So it's a bit like you can imagine the quarks are held together by elastic bands. As you pull them apart, normally, as you pull them apart, that interaction gets stronger and stronger. And it would take an infinite amount of energy to pull them really properly apart. So you can't do that. And so we don't ever see individual up quarks and individual down quarks. Instead, what we see is bound combinations of them called protons and neutrons. So protons and neutrons are made out of quarks, and they make up. This is a little sketch of a nucleus of an atom. Sorry, there's this cloud of electrons around the outside, and in the middle there are protons and neutrons. Okay, and if we go back to that original picture we had of all those quarks and leptons and force particles, as far as we know, those particles are indivisible. They are point particles. They have no extent. They have no size, and they can't be split into anything smaller. And experimentally, as far as we know, that's the bottom. You can't get beyond that. But what I'm going to show you today is that if we put very large numbers of particles together, strangely enough, we can use that to split these apparently indivisible particles. So, oops, I need to say something else. So these four particles are described by a very small number of properties. Every electron is exactly the same as every other electron. Every proton is the same as every other proton. Every neutron is the same as every other neutron. And every photon is the same as every other photon. And they're described by basically four properties. They have an electrical charge, so -1 for the electron, +1 for the proton, and 0 for the neutron or the photon. They have a mass, which is given in these rather strange physicists' units, so don't worry about the units, basically, but they have a mass, and it's 0 for the photon, which is why it's not written on there. And they have this property called spin. You see it's spin 1/2 for each of the matter particles, and it's spin 1 for the photon. Okay, and we need to understand, it's going to be important for the rest of the talk that we understand what spin is. And so when physicists first discovered this thing, spin, it looks like a kind of angular momentum, and physicists assumed that these particles must have some size and be spinning like this top. And that's absolutely, we now know what spin isn't. Right? So spin is a strange quantum mechanical effect, which there isn't a really simple, intuitive picture for, but we know that as far as we can tell experimentally, the electron and all the other fundamental particles have no size, so there's nothing that could be spinning like this spinning top. And so this is completely the wrong picture. The only picture that makes any real sense is to imagine there's a tiny little magnet tied to each electron, and each electron has that tiny little bar magnet stuck inside of it. And so you can think of if there were something spinning, it would be spinning around the axis defined by these arrows. And so in the rest of the talk, by and large, I'm not going to draw little magnets everywhere. I'm going to draw these arrows, and that's just representing the magnetism associated with the electron. Okay, and if you see a bulk magnet like this, and this is actually the hardest bit of the talk. This magnet is very strong and very hard to get off of this. What's happening in this magnet is that many of the electrons are aligning their tiny little magnets with one another like this. And all those little electrons working together make the magnetic force that's coming out of this magnet, and are what are able to work together to overcome the gravitational pull of the entire planet. And so this is basically, an example of a classical magnet. And we're not going to be interested in classical magnetism very much today. We're going to talk about quantum magnetism, which is one of the things I like to think about all day. And we can get this kind of quantum magnetism like this, where instead of aligning with each other, we take a one-dimensional array of electrons on some lattice, and they align in the opposite direction to their neighbor. So there's no bulk magnetic field coming out of this, but we get some kind of pattern like this. And there's a very simple experiment you can do. You can take a laser and shine it on your material, and you can kick out one of the electrons. So if you think of the system we had before as our ground state, or as physicists like to call it, our vacuum, then we have a little bit less electrical charge where we've kicked this electron out. And we've also made some defect in the spin. So there's something weird going on in the spin. There's some spin missing as well. So some charge missing and some spin missing. Now, if I confine these electrons so they can only move in one dimension like this, there's not going to be very much energy required to take an electron and hop it on to the empty site, like that. And so that's the kind of thing that will happen if there's some thermal energy in the system. Okay, and now what we've done is we've moved the charge here, and the kind of discontinuity in our spin has now moved over here. So we've started to push the spin and the charge slightly further apart. If I hop the next electron over as well, the charge has moved and the spin has changed, has stayed where it is. And so what I'm doing is, if electrons keep hopping, then this charge starts to move off by itself. And another thing I can do is flip those two spins together. And you see my defect where I had two spins pointing in the same direction moved off by itself. And so both of these processes can go on independently. And one thing to notice is the spin moves faster than the charge. The spin moves 2 sites every time I move something, whereas the charge only moves 1. And these things carry on moving around. And in this cartoon I've shown you, we can see that the spin and the charge begin to move independently of one another. And if you really sit down and do the quantum mechanics, it turns out this is a problem we can solve exactly in quantum mechanics. There's very few problems we can solve exactly in quantum mechanics. This is one of them. And it turns out that the spin and the charge, quantum mechanically, really behave like particles. So the mathematical description of them is exactly the same as the mathematical description of the electron in the vacuum. And so these two particles have been called the spin-on and the hole-on, because there's a hole where this is. And these are particles in exactly the same sense. They appear in exactly the same type of theory called a quantum field theory that describes the standard model of particle physics. And so what we've done here is we've taken an electron, which particle physicists will tell you is an indivisible particle. No one's ever split it in the vacuum. But by putting it in a material, we've split it into a holon, which has charge but no spin, and a spin-on that has spin but no charge. And particles like this don't exist in the standard model. In particular, there's nothing that looks like the spin-on, and there's nothing that has charge and no spin. So because we've got this huge numbers of particles, we can get something fundamentally new, something fundamentally different than we see from individual particles. Okay, and the way we can do this experimentally is to look at crystals. So my sons are very excited about wizards and crystals and their magic powers, and that's, well, I think crystals are pretty close to magic. I don't think they're literally magic. So this is a picture. This could be, for example, a crystal of table salt would look a bit like this. So you can imagine some of these atoms, the green ones, say, could be sodium, and the purple ones could be chlorine. And this is the way in table salt the atoms pack. But there are many different examples of crystals we can make, and some of them we can even make out of organic materials. And this is an example here. And so this is actually a material that has some organic part, which is these rings, and some metals. And these actual materials, this is called copper pyrazine. This is a beautiful, actually, experimental example of this theory I told you about before with the holons and the spin-ons. And you can really go experimentally and see the individual spin-ons in this material. And the reason it's very one-dimensional is the magnetic interactions through the chemical bonds turn out to be very strong, whereas the magnetic interactions, so the unpaired electrons are living on the metals, and the magnetic interactions through space turn out to be very weak. And so we get strong magnetic interactions along the chains and very weak interactions between the chains. But eventually, at low enough temperatures, the interactions between the chains become important, and we get this kind of classical magnetism I talked about before. And we lose all our quantum fun. So normally we think of crystals as being very rigid. But my friend and colleague Jack Clegg in the chemistry department at UQ showed that isn't always the case. So this what you're seeing here is a pair of tweezers, some kind of pointy, I don't know what that pointy thing's called. But this is a crystal. This whole thing is a single crystal. And as it bends, the crystallinity doesn't change. So we still have a beautiful periodic array, and it bends entirely elastically, and when you release the force, it springs back to the way it was before. And so normally, if you have a crystal, it's very hard, and if you try and bend it, firstly, it's hard to bend, but if you do succeed in bending it, you break it, right? And engineers are very concerned about defects in crystals because that's the way they break. But there's nothing. This is entirely elastic and going on because of these organic molecules that are very large. And I had a very talented PhD student called Elise Kenny, and she started thinking about this material with me. And what she discovered is that as well as being an amazing flexible crystal, it's also a beautiful example of this 1D quantum magnetism. So this is, as well as being incredibly flexible, it's also one of these 1D quantum magnets. And the reason is because the interactions between the chains are very strange. They form these triangles like this. So the spin here is up, and it would like all its near neighbors to be spin down. So within the chain, it can kind of do that. But because we've got interactions along the triangles, this one would like to put a down spin here, but this one would like to put an up spin here. So we don't know what to do. The crystal doesn't know what to do. And this actually suppresses the classical magnetism down to temperatures that are too low to measure. So experimentally, you never see this classical magnetism emerging. It always stays quantum mechanical. But what's even more remarkable, is, at least found, is when you start to bend the crystal, this cancellation starts to go away and becomes imperfect. And so you can imagine bending the crystal, it eventually goes from a non-magnetic state to a magnetic state, and this poor little incredible Hulk gets sucked up by the giant magnets above him. Okay, and that's kind of fun, but what's really remarkable about this discovery is the amount by which the temperature at which it becomes magnetic changes when you bend it. So it increases 1,000,000,000,000,000,000,000,000 times. So it's 10 to the 24, if you like that notation, 1 with 24 zeros after it. Now that's an unimaginably large number. I can't get my head around it, so I tried to have a think of something else that's 1,000,000,000,000,000,000,000 times bigger. So this is my example of something else that changes that much. So think about the size difference between a fly, so that's a millimeter or so, and a suburb. Right? A suburb's a kilometer or so, a few kilometers, maybe a few millimeters for the fly. So that's about 1,000,000 times difference in size. That's 1 million. So we need to find something that's 1,000,000 times bigger than a suburb, and you can do that. That's the sun. It's about 1,000,000 kilometers across. So now we've got the sun is 1,000,000,000,000 times bigger than the fly. Okay, so we need something that's 1,000,000 times bigger than the sun. You can do that. You can take the solar system. If you take the normal solar system, whether you include Pluto or not in the solar system, it's not really big enough for us. So we need to include the Oort cloud, which is like gas and little rocks and things that go out a long way past all the planets and dwarf planets and things, way past the Kuiper belt. So the Oort cloud's about 1,000,000 times bigger than the sun. So the Oort cloud is 1,000,000,000,000,000 times bigger than the fly. Still not big enough for us. If we take the Milky Way, this is not the Milky Way, but it's a pretty similar looking galaxy, that's about 1,000,000 times bigger than the Oort cloud. So the Milky Way is 1,000,000,000,000,000,000 times bigger than a fly. And that's the scale difference we get in the temperature at which this system becomes magnetic. Oops, what happened there? Becomes magnetic when you bend it. And as far as I know, this has not been fully confirmed experimentally yet, but if it comes through, then this is, as far as I know, the biggest change in any material's property by some external stimulus. Okay, so that's enough of me talking. I promised you earlier that I would show you something quantum mechanical that you could see with the naked eye. So you can see it with the naked eye. I think people at the back might have a little trouble because it's not that huge. So there's a camera over there. It's just going to show you what I'm doing. Okay, and also shows you that many-body physics is essentially magic. Okay, so I have my magnet from before, and in here I have some superconductors. And superconductors do really remarkable things. So in here, I should say this: the contents of this is incredibly cold. It's about minus 200 degrees Celsius. Which us low-temperature physicists call these materials high-temperature superconductors. The reason being that until these were discovered in the mid-'80s, and before then, you needed to go down maybe another 50 Celsius or so, and that's incredibly expensive. You need to have liquid helium, which is very rare. Very expensive, costs thousands of dollars a litre, whereas liquid nitrogen is cheaper than milk, and so the University of Queensland will allow me to play with it in front of you this evening, whereas they won't give me liquid helium to play with. Okay, so they do really amazing things. So So if I put this on here, where's the camera? Bring it down here. This superconductor is levitating. There's nothing in here. I can sit that underneath. There's nothing in there, nothing around, nothing holding it up. If that doesn't impress you enough, I can turn it up. Whoops, I can't turn it upside down. Left it too long. Let's get another one. Put it on. Let's not do it over the liquid nitrogen in case it goes wrong again. And there we go. It's stuck on by the magnet. I mean, that's nothing you can't do with magnets. So here I have two more magnets. They're in these circles. Oops, here I have two more magnets. They're in the circle like this. If I put them on here, if I got that right, they'll start to spin. Last time I did this demonstration to primary school kids, they said this is the world's coldest fidget spinner. And this will basically go on for a very long time because there's very little friction. Okay, there's only friction between the superconductor and the air. There's no, because it's not touching the magnets below it. There's no friction there. So I got bored of waiting for that to finish. So what I have over here is another ring of magnets, and they're just in a big circle like that. I think you can see on the screen all these little silver dots are magnets. I have a slightly bigger superconductor over here. If I can get it to go on. There we go, it's keen to start going. Give it a little push down. It's quite hard to get this on, it doesn't like the super. And there we go, going round. And that will go, you see I gave that a tiny little tap. You can actually see the table's not completely flat, the way it speeds up and slows down a bit. And that's levitating. And that's one of the things we might think about using superconducting technologies for making maglev trains. Right? If you had a train running on this, it had incredibly low friction, only air resistance, and you can see I've given it a tiny tap and it's still going. And so this could make incredibly fuel-efficient trains. The problem at the moment is you need to cool these things down to minus 200 degrees Celsius or so to get them to work. That's getting a bit too hot. So that gives us one of the holy grails of condensed matter physics. It's too hot. Let's put it back in there, cool it down again. I think I haven't used this one. Let's see if it works with this. That wants to go up. One of the holy grails of condensed matter physics is to make a room temperature superconductor. There we go. That's not going to go for very long, I don't think. Is to make a room temperature superconductor. That could have incredible uses, not only making maglev trains, but also superconductors carry electrical current. The reason they get their names, they carry electrical current with no electrical resistance. When you generate electricity, a huge fraction of it is lost when you transport it from the power plant to your home, to your business, wherever you're going to use the electricity. If you could replace all those copper wires with superconducting wires, you could put panels of solar panels, cover the outback in solar panels, and then transport it losslessly into capital cities for people to use. So it would be incredible if we could get room temperature superconductors. Also, we'd like nice materials, properties of those room temperature superconductors, because one of the reasons this technology has not really changed the world is that it turns out the materials are ceramic and are very difficult to work with for engineers. Let's see if this is cold enough that it'll go again. Yeah, that feels good. Give it a push. Okay. There we go. That'll run for some time. I'll just leave that going. So superconductivity is an entirely quantum mechanical phenomenon. You can't explain this classically, so if you really want to understand it, you need to take 3 or 4 years of quantum mechanics at university, but I'll do my best to explain it without that. So could we put the slide back on and start the video? So the nicest explanation I know of superconductivity without using too much quantum mechanics is through interpretive dance. I'm not going to dance for you. The dancers are up here. Okay. So what I want you to imagine is that these people are the electrons moving through a wire. Right? So you've turned on your phone or your iPad, and electrons start flowing through wires. And that current, that electrical current, is just all the electrons moving through the wires. And the electrons have to avoid each other. They don't like to bump into each other, just like people don't. And they also have to avoid furniture, which is little impurities and imperfections in the wire. And that's what gives us electrical resistance, the electrons having to stop and slow down and get through the crowd, walk around and not bump into the table. So in a superconductor, if we cool it down cold enough, we go through a point labeled Tc here, which is the mathematical symbol. It stands for critical temperature. It's the temperature at which the material becomes superconducting. And what happens, first of all, the electrons enter this kind of quantum dance where they pair up with one another. So you can see in here, everyone with a matching colored hat is dancing with their partner. Actually, the quantum mechanical dance is much more complicated and beautiful because the two electrons are dancing in different directions in time. One's dancing forwards in time and one's dancing backwards in time. I think we can forgive the choreographer for not capturing that aspect of superconductivity. But you see they're kind of mirroring each other, which is, I think, what they're trying to capture. Okay. And so eventually you get more and more electrons forming these pairs. And in quantum mechanics, pairs of electrons behave in fundamentally different ways than individual electrons. So no two electrons are allowed to go into the same state, something called the Pauli exclusion principle, which is the basis of chemistry and hence life, so it's pretty important. But pairs don't obey that rule, and so they can all go into the same quantum mechanical state, and that's basically them all synchronizing together. They make a giant quantum mechanical wave made out of electrons. So just the same ways you get waves in water that are made out of the molecules of the water ultimately, you can get waves in an electron fluid where you get this kind of synchronization of the motion of all the electrons. And that turns out to be essentially how a superconductor works, how it can carry current with no electrical resistance because the electrons are dancing beautifully together. So when you turn on a current, the electrons move in this beautiful synchronous way. They no longer have to worry about bumping into each other because they know what the person in front of them or the electron in front of them is going to do. It's like a beautifully choreographed dance. And so they can also arrange their dance so that it goes through the areas where the impurities, the chairs and the tables aren't. So they don't bump into each other. And that's essentially how the electrical current is carried without any loss of power, any loss of energy in a superconductor. Okay, so why does that allow the superconductor over here to levitate? That's how we have zero electrical resistance. But really, actually, physicists like to think of this levitating property as the fundamental property of a superconductor. Because if you have this levitating property, you can show that you must have no electrical resistance, whereas the opposite isn't true. So what happens, essentially, oops, wrong button. Not used to this remote control, sorry. These lines, these arrows here are supposed to represent the magnetic field, the magnetic force coming from the magnet. And this circle is a metal. If we have an ordinary metal, and superconductors become metals when they're not superconducting, that's actually what's going on over here now. You see this thing's fallen down. It's turned back into a metal. It's gone above its critical temperature. Then the magnetic field just goes straight through. It doesn't get impeded by the metal, essentially. And so really the metal doesn't care that there's a magnetic field very much there. However, in a superconductor, when you put the magnetic field on, that generates a supercurrent going around the surface of the superconductor. And that superconductor can flow without electrical resistance. Actually, the same thing happens when you turn on the magnetic field on a metal, but it dies away very quickly because of the electrical resistance. Whereas in the superconductor, it keeps going forever. And so the magnetic field can't get through the center of the superconductor. It has to go round the side. But it doesn't like going round the side, and so it pushes back. And that magnetic field pushing back is what levitates the superconductor. Okay, and what's really interesting, though, is what's happening to the photon inside the superconductor. So the photon, as we saw before, has no mass in the standard model of particle physics. And if we go back, the one way to think about why the magnetic field can't get in is that the photon actually generates a mass. So the interaction with the electrons, in that wave of electrons between that interacting with the photon gives it a mass. Much like if you tried to lift this weight, it's quite heavy, but if I tried to lift it in a jar of treacle, it would feel much heavier. Right? That would increase the mass. And so that, in a very similar way, that interaction between the supercurrent and the photon actually gives the photon a mass within the superconductor when it doesn't have one fundamentally. And that has quite a famous name. That's called the Anderson-Higgs mechanism. And so Phil Anderson, who's a Nobel Prize winner, explained that this is what's going on inside of a superconductor. And Peter Higgs said that, well, this could explain a puzzle in high-energy physics if you had a very similar mechanism of why the W and the Z, the weak bosons that are responsible for radioactivity, have a mass, whereas we expect all the other force carriers not to have a mass. And what Peter Higgs pointed out as well is that if that were true, if an Anderson-Higgs type mechanism, so the universe is superconducting essentially, were true, then you'd have an extra particle in your standard model, which is called the Higgs boson. So when people say that the Higgs boson gives mass to all the is responsible for mass, that's not really quite true. The Higgs boson is responsible for giving mass to the W and Z bosons, and then the coupling of the matter particles to the Higgs boson gives these matter particles Higgs. That's only actually responsible for about 0.1% of your mass. Most of the mass of your mass is coming from the energy holding the nuclei together, the up and the down quarks, and bound together by gluons. And it doesn't really come from the Higgs. The Higgs is just the signature that that's the correct physics. So it's very important to discover, but it doesn't actually play a hugely important role. So one thing that's puzzled physicists for a very long time is if you look at this chart, we have electrical charges. All of these particles have an electrical charge, but we don't see any magnetic charges. And in fact, you may have discovered this for yourself when you were a kid. If I were to take a bar magnet like this and cut it in half, I wouldn't get a south pole. If I cut it along here, I wouldn't get a south pole up here and a north pole down here. I'd get a new south pole here and a new north pole up here. So I can't split this magnet into individual south poles and north poles. And if I did, those would be magnetic charges. Physicists like to call them monopoles because a magnet like this is called a dipole. But all the magnetic monopole is the magnetic charge. And in the theory of electromagnetism, electricity and magnetism really look exactly the same, except for this problem that there aren't any magnetic charges and there are electrical charges. And there's no real good theoretical understanding of why they should have that difference and no other differences. The maths would look much more beautiful if we have magnetic charges as well. And what's more, if you try and derive grand unified theories, if you try and combine quantum mechanics with gravity, it seems like you always, or very often, every effort we've had so far, you always turn up with magnetic monopoles, with magnetic charges that we don't see in the universe. And so there's been a huge experimental effort to detect these magnetic charges. And despite decades of research effort, millions of dollars spent on it, no one has found a magnetic monopole. Until we changed where we were looking and started looking, instead of looking for individual monopoles, looking for monopoles inside of materials. And actually about a decade ago, magnetic monopoles were discovered in a set of materials called spin ices. So this is a little cartoon of what's going on in a spin ice. So it's a little more complicated than the magnetism we looked at before, But they follow, actually, this diagram that looks very random is following a simple set of rules called the ice rules. So if I look at one of these triangles like this that points up, then there are 2 spins pointing out of it and 1 spin pointing out in. So I go to another one pointing out, 2 pointing out, and 1 pointing in. 1, 2 pointing out, 1 pointing in. And hopefully if I've drawn this diagram correctly, you can go to any of those up pointing triangles and find there's 1, 2 pointing out and 1 pointing in. However, if you look at the down triangles, they follow the opposite rule. Right? So there's 1, 2 pointing in and 1 pointing out, 1, 2 pointing in and 1 pointing out. And as you can see, there's lots of ways you could do this. There's many ways you could do this, and that allows us some freedom. So we can think about what would happen if we were to flip just one of these spins, one of these little electronic magnets. Well, what we'd do is make a little extra south pole up here and a little extra north pole down here compared to the state we had before. Okay, so then you might think, oh, well, I want to fix that up. That's not the best situation. The material likes to be following the ice rules. So maybe I'll flip some more spins. And what you see happens is the south pole moves off in one direction and the north pole moves off in the other. And again, we can do the full quantum mechanical calculation, and you find that these are actually free particles moving independently in exactly the same sense as the free particles in the standard model as electrons and quarks and so forth, except they only exist within the material, they don't live within the vacuum. And it's up to you if you think that is fundamentally different, or whether you think it's really the same, whether you're a vacuum chauvinist, or whether you think all materials are made equally. So we can carry on flipping this. And now this south pole's got to the edge, and something really interesting can happen. We can flip this spin on the end, and we've restored the ice rule up here. So now we only have one north pole. We have a single free magnetic monopole moving through the material. And we've got these magnetic monopoles living within a system with very large numbers of particles that can't exist within the vacuum. Okay, carries on moving. Okay. So I hope I've convinced you that materials where we have enormous numbers of particles can be more than the sum of the parts. I've shown you that quantum mechanics allows us to do things that are essentially indistinguishable from magic, from levitating superconductors going round. I've shown you how we can change the properties of magnets by bending them and increase them 1 million. How many millions did I say? Lots. Increase them as much as the difference between a fly and the galaxy. But also I hope I've shown you that materials can be less than the sum of their parts. So I've showed you the standard model where we have electrons, and the electron is an indivisible particle according to our fundamental theories of physics. Yet in materials we can split it. We can split it into a spin-on that has spin and no charge, and a holon that has charge and no spin, 2 particles that don't exist in the vacuum and can't, as far as we know, exist in the vacuum. I've shown you how we can get magnetic monopoles, particles that have been looked for extensively in the vacuum and never found. So I hope I've told you that more is different.
Amazing, Ben. Thank you so much. We'll give you a moment to catch your breath. Now is your opportunity to ask questions. The secret of the universes, secrets of the universe, just one I think, are right here for you. There is the QR code that you can access. A couple of little bits of housekeeping. Don't forget this talk and many others before it will be available on YouTube in the next week or so. So if you're looking for your evening fix of science, make sure you check out some of those fantastic speakers. We are, of course, back again next month for our final BrisScience session of the year. We're doing something a little bit different for December. We are going to have a science comedy panel show, think like QI, Spics and Specs. So we're going to have 6 amazing scientists, a few BrisScience regulars. You might have seen this year or last year. We've got Tamara Davis, eminent astrophysicist, back. And they will be battling it out with wits and wittiness to try and uncover the big stories of the year. So I'm hosting that one. It's going to be a lot of fun. Make sure you grab your tickets early. Really hoping we pack the place out. That's my pitch. Okay, are you ready for the questions, Ben?
Sure.
All right, so questions here. Okay, look, first question is from Ben, who asks, do we think a room temperature superconductor is physically possible?
Okay, so that's a great question. So there was a paper back in the 70s which purported to show that it was impossible to get superconductivity above minus 230 Celsius or so. So I've just shown you a counterexample to that theory, which was discovered in the 80s, so that was wrong. So I don't think there's any fundamental reason you can't, but to date, progress has been basically driven by luck, by not knowing. So these so-called high-temperature superconductors were discovered by people who they were looking for superconductivity, but actually the theory they were using that told them to go look at this, we now know is completely wrong and doesn't explain what's going on. So there was a lot of luck in the discovery of those. And something actually my group works on at the University of Queensland is we're really trying to understand how in principle could you use organic chemistry, the kind of molecules I showed you a bit in these flexible crystals, how could we use that to design materials that would have higher temperature superconductivity? And so I very much hope the answer is yes.
Great answer. I'll go sort of one more of the easy ones before we move on to the deep stuff, which is how much do superconductors cost per kilogram, per kilometre of rail track from Jenny?
Oh, I do not know. That's a good question. So it depends.
It's nice to be so rich you don't know the price of a loaf of bread, a superconductor.
Right. So, well, it depends very much on what superconductor you're thinking about. So almost all metals superconduct if you make them cold enough. There's a very few exceptions. For example, gold is one that I can think of. But almost everything will superconduct. So if you take lead or aluminium or niobium and cool them down, they will eventually superconduct. These things are a bit more complicated. They're ceramic. The materials, the basic base materials that are going into them aren't so expensive. Most of the cost is the fact they're produced on a pretty small scale. There are certainly that's not what has stopped large-scale applications of superconductivity. So people have seriously thought about building wires out of superconductors, and they have been used in some places. One of the other advantages of superconductors is they can carry much higher current densities than copper. Copper will melt. So the place they've been used is in like large trunk distribution kind of places where you're already paying a lot to cool copper. So normally you cool copper with oil, which of course is a problem if you have a leak. Whereas if you're cooling with liquid nitrogen and you have a leak, well, most of the air is nitrogen already, it doesn't really matter. So it's not prohibitively expensive from a technological point of view, but I'm sorry, I don't know the numbers off the top of my head for these.
Great answer. Okay, Mark asks, first he says, thank you, Professor Powell. You mentioned during the electron dance that electrons pair, but one moves forward in time and the other moves backward. Can you possibly explain that using layman's terms?
Okay.
Can we lock the doors, please? We've got another hour lecture now.
Okay. Can I explain? Maybe the answer is no. This gets to the heart of really the detailed theories. Okay, I would normally not try and explain this to undergraduate final year physicists. I'm going to give it a go, and if I apologize if I get completely lost, if I completely lose you, or if I get lost as well. Okay, it turns out in quantum mechanics, so probably you've heard of matter and antimatter, right? So what the modern way of understanding antimatter, and it's mathematically equivalent to any other way of understanding antimatter, is that antimatter is just matter going backwards in time. So the rules of quantum mechanics are the same whether you go forwards or backwards in time. One of the great puzzles of physics is why do we experience time the way we do? In terms of fundamental physics, the basic physics equations that govern the universe, the theory of almost everything, should look the same whether we run it forwards or backwards in time. But that's obviously not our lived experience of the universe. And so the only possible answer is that this breaking of the symmetry of forwards and backwards in time is an emergent phenomenon. Right? It's coming from the complicated interactions between particles. And as far as we and that's connected with ideas about entropy, about how the universe tends to get more disordered over time. Okay, so the superconductor doesn't really is cold enough, there's not a lot of entropy around, and it turns out, okay, an alternative description of antimatter is that there's a huge number of electrons everywhere, but we don't notice them, and you've picked one out. And you can think of that, you can think of that in a metal. A hole where there isn't an electron behaves a bit like an electron going backwards in time. And so in the superconductor, you can think of the pair being made of a hole, where there was an electron before we've taken it out, and an extra electron I've added in. And so the electron is going forwards in time, and the hole is going backwards in time. But actually, when you do the quantum mechanics, it gets much worse than that, because we get actually what happens when they pair is you make a quantum mechanical. Each of the particles becomes a quantum mechanical mixture of a particle that is there and a hole that isn't there, partly going backwards in time and partly going forwards in time. And this is why I don't try to explain it to undergraduates.
That was a great answer. There will be a test on this afterwards, so... okay, let's go a little bit more localised. We have a lot of questions here. I'm going to try and get through some. So questions about the levitation. Wes asked, what properties dictate the height of levitation? And Richard asked, can that spinning, levitating superconductor be pulled off course with the magnets that you have?
Oh, that's a good... We should do the experiment, right?
Richard, you just wanted to see the superconductors again, didn't you?
So that one's going to be hot. I've never tried this. Let's find out. This is why we do physics, not maths, because it's an experimental science. Right, so I do that, and then you want to put a strong... Oops. Yeah. So no, it's not pulling off course. Okay, I think I can explain why that's happening. Okay, so I told you, again, a slightly simple version of the story with the... So a question we could ask as well that's related... so can I pull it off course? It's why doesn't it fall off course all the time, right? If I just took two magnets that repelled each other, you've all played with magnets as kids, I assume, they push each other apart, but it's unstable, they tend to fall off, right? So actually something more complicated is happening than the simple picture I showed you. As well as being distorted around the side of the superconductor, what the superconductor decides to do is to let some of the magnetic field go through, and it makes what's called a little vortex. There's a little bit of magnetic field go through the middle and has a supercurrent running around the outside to screen it. So it makes its own little edges inside of there. And energetically, the best place to put those vortices is where there's some impurity in the crystal, and so there's less superconductivity there. So it costs the system less energy to put the vortex on an impurity. Okay? And so then if I try and fall off to the side, that's going to cost me energy, and so that results in a force that keeps me on the side, keeps me on the straight and narrow, and I don't fall off. Okay, how high it levitates is basically a function of how hard I pushed it, was the other question. So if you notice, these things are actually quite hard to get on. They'll float. I can get them to float really high, but that's really unstable. If I give that a push, it'll probably fall off because it's only just on the... So when I do the demonstration, I push it down a bit. Probably pushed it too hard because it's quite warm now. It's not going to play ball. See if this one's ready to go again. This one you really have to push quite hard. Oops. Right, see it does that because I haven't pushed it on enough. So I have to push it down. And there I'm putting energy into the system, right? I'm pushing. I'm providing the force to get it down, and really the superconductor doesn't want its magnetic field to change, is really what we should say. That is not cold enough. I don't think it's going to stay on. But you can see maybe the struggles I'm having, like that tiny push so I don't break it. And it's that, yes, so it wants to stay where it is, and that's what determines how high it is. What it really wants is the magnetic field to stay how it is. It doesn't like change. Like all sensible people, it fears change.
Okay, great. So you got energy for a couple more questions?
Sure.
We're almost at the end. Okay, this one's fun. Mark wants to know, could Pluto or other cold celestial body, notice you didn't call it a planet, well said, Mark, could Pluto or other celestial body act as a superconductor?
That's a great question. So actually, one thing I said, room temperature superconductors could change the world. I will get to answer the question. But actually, another caveat I should have is room temperature ambient pressure superconductors. So we have actually achieved superconductivity at room temperature in the last few years, although there's actually now some controversy about those papers, and they might be about to be retracted, so they might not be true, which is science correcting itself, which is a good process we should be happy about, finding mistakes in the literature. But anyway, there are certainly claims that if you put hydrogen sulfide under enormous pressures, that superconducts at very high temperatures. And one of the reasons people started thinking about this is to do with the center of Jupiter, where the pressure is at, there's hydrogen at the center of Jupiter, and the pressures are absolutely enormous, much higher than anything we can achieve on Earth. And some people believe the core of Jupiter is already superconducting. The other place where we find, well, not quite superconductivity, something very related called superfluidity, is in a neutron star. So neutron stars are very hot, but again, enormously high pressures. They put the pressures in Jupiter, in the center of Jupiter, to shame. They're enormous high pressures. So that although they're stars, they're very hot objects, right? It's believed that they are superfluid. So basically, they're superconductors without an electrical charge. They're made of neutrons, which are electrically neutral. And you can see neutron stars often become pulsars, and it's very difficult to explain the pulsar behavior if you don't have the star being a superfluid. So we believe, yes, there are probably several examples of superconductors in celestial objects, but we don't have direct experimental probes of those things because they're very far away and hard to look at.
Amazing. All right, second last question. Asif, who is 8, asks, can a spin-on and a hole-on meet? And if they can, what would happen?
That's a really wonderful question. I think Asif, however I correctly pronounce your name, you're destined to become a physicist because that's exactly the kind of questions that physicists love to ask. And so what would happen is they would combine back together again to make an electron, or the original hole we had, and there'd be some energy left over when they do that, and so that would tend to come out as light. So actually one of the ways you can see these things experimentally is to look for that light coming out.
Amazing. All right, and final question, Ben, this is Chair's prerogative. Let's say that Elon Musk, instead of buying Twitter, had come to you and said, I can't think of anything to do with $46 billion. Do you have any suggestions? What would you, and let's keep it within your field, no, like just buy me an island, but what would you do?
So the question I would go at really seriously is, can we have a room temperature superconductor? I think it would have. I mean, this is very much my personal opinion. I think lots of people in my field would disagree with this, but I think we're at a stage now where we understand sufficiently well how these high temperature superconductors work that we can take the principles that we understand about them. There's a huge controversy about how these work, I should say. And part of that controversy is sociological because everyone knows whoever explains how they work and convinces everyone else they're right will get a Nobel Prize. So there's lots of people very entrenched positions. But I think we understand most of the basics. We understand what the material properties we need are to get room temperature superconductors. And I think certain developments have happened in chemistry. That means you can then think about going and designing materials with those properties, which I don't think you could until the last 5 or 10 years. And I think there's a real problem that physicists and chemists, physics is hard, chemistry is hard, very few people understand both. Physicists and chemists have a tough time communicating with each other, right? And so I think I would spend all that money on a big interdisciplinary institute bringing the best physicists and the best chemists together to work really seriously on this problem of how you make a room temperature superconductor.
Amazing. Great. Please join me in thanking Professor Ben Powell.
Thank you very much.
I think that may be the longest applause in the history of BrisScience. So fantastic talk. That was a brilliant talk, Ben, and thank you for sharing those insights tonight. I know there's a lot more questions there. I'd love for you to join us outside. However, before we leave today, I'd like to invite Kristen up on stage. Kristen is from the Australian Research Council, one of their quantum excellence research centres, with a competition. Would you like to...
Sure. Hi everyone. I'm Kristen and I work at the Australian Research Council Centre of Excellence for Engineered Quantum Systems. If you want to know how to spend $46 billion, you could fund 1,000 of those, and probably just one in superconductors might get the answer, so tell him to bring the money to the government. But anyway, I'm here. Our centre is based at the University of Queensland, and our researchers use these weird quantum properties that you've just heard about to build technologies of the future. But the reason I'm talking to you now is that we're also running a quantum art competition on the theme of emergence. So if you know any artistic types, or if you are yourself an artistic type, the prize money up for grabs is $5,000, $3,000 for first prize, $1,500 for second prize, and $500 for a People's Choice Prize. You can do any medium of art you want, paintings, theatre, interpretive dance. It just has to be able to be submitted through our website, so like a photograph of a painting or a video of an interpretive dance. Entries are open until the 14th of January 2023. If you have any questions, we've got some posters. I'm going to be sticking around. You can ask me some questions. But yeah, I just wanted to promote our competition.
Thanks so much. Thank you, Kristen. And please join again thanking amazing Ben Powell.